All right. Good morning, everybody. Hope you guys are doing well today. Um, we are going to start discussing the next section of exponential and logarithmic equations, which is chapter 5, section 4. And really, this is just going to be using some of those rules that we've learned in the past couple of sections to solve some exponential and logarithmic equations. So let's get started. There are two basic strategies for solving exponential or logarithmic equations. The first one is based on the one-to-one property and was used to solve simple exponential and logarithmic equations. And you've already done some problems in the previous couple of sections using the one-to-one property. The second one is based on the inverse property, which the inverse property is what allows us to move something from exponential form to logarithmic form or from logarithmic form to exponential form. They call it the inverse property. The other way you could think of it is literally the definition of a logarithm. And it was the very first property that we discussed when we first started talking about logarithms. So the one-to-one property says if you have a, which is any base, to the x power, and it equals a, the same base as the first one, to the y power, if and only if x equals y. And that's obviously because a's are the same, therefore the exponents have to be the same. In this one, it also states if you have log base a in both of the equations, and you're logging something, the x and the y have to be the same if the log and the base are the same, if these are said to be equal. The inverse property allows us to take something from exponential form and put it into logarithmic form. I'm not going to use this inverse property so much per se as I am going to use the definition of a logarithm. So how to go from a logarithmic form to exponential form. I think that's the easiest way to do this. Okay, so the first one, first example I have for you has about 7 or 8 different problems in it. So let's take a look. So the original equation is 2 to the x equals 32. What you want to do first is you want to get the bases to match. So in this case, we have 2 to the x. We need to rewrite 32, so it's a power of 2. So when we do that, you move to the next column here. You have 2 to the x equals 2 to the fifth. So 2 to the fifth is 32. Now you can see the bases match. Therefore, the exponents have to match, and we are able to solve this saying x equals 5, and that's using the one-to-one property. Now, you guys have already done problems like this in prior sections, so this shouldn't be too hard for you. The next one is natural log of x minus natural log of 3 equals 0. And this one is solved simply by adding natural log of 3 to both sides. So you will end up with a rewritten equation of natural log of x equals natural log of 3. And since you can see the natural logs are just log base e's, so the log and the base are the same in both sides of the equation, therefore x has to equal 3, and that is also using the one-to-one property. Now, part C is a little bit more difficult. Students tend to struggle with these a bit because of the fractions, because to me, it's not immediately obvious what to do at first. You can see we have this 1 over 3 to the x, and then we have the 9. Now, what you have to try to do is establish or think in your head, what is the base number that's being taken to a power? And the 9 is probably a little bit easier to recognize. Within that 9, it's going to get rewritten as 3 to the second power, as you can see right here. Now, this one is not so obvious. So what's going to happen is this is actually 1 over 3 to the first. This 3 in the denominator would come to the numerator, and it would become 3 to the negative 1 power. Now, following that, once the 3 comes up and it's 3 to the negative 1 power, you have a power to a power. You have 3 to the negative 1 inside parentheses, and then on the outside you have an x. When you have power to power, the powers need to multiply. So 3 to the negative 1 to the x, negative 1 times x is negative x, and that's where that negative x comes from. Now you can see we have it rewritten with both of the same numbers in the base. So now we can say that their powers are equal. And you can see negative x equals 2, which means x equals negative 2. All right, so for the next part D, you can see we have e to the x equals 7. This one's a little tricky because it is not using the one-to-one property, it's actually going to use the inverse property. So what you can see is we have this exponent, we have e to the x, and it equals a number. Anytime the variable is in the exponent position, and it's a variable, you automatically should think in your head, we need to take this from exponential form and put it into logarithmic form. And the way that you're going to do that is you're going to utilize the very first log property that we learned to move it from exponential to logarithmic form. So you can see the base of this exponent is e, the base of the log becomes e, and then basically the x and the 7 switch places. So it becomes log base e of 7 equals x. And that's actually the solution. That's the one nice thing about doing these problems is as soon as you take it from its exponential form to the logarithmic form, you have your solution. Part E is very similar. We have natural log of x is equal to negative 3. So this is the exact opposite of part D. D, it was in exponential form. You had to put it into logarithmic form. In this case, it's in logarithmic form for part E, and we're going to put it into exponential form. So this is log base E. That's what natural log is. So that it's E, you start with the base, and then it's to the negative third power is going to equal x. And you can see right here we have e to the negative third power equals x. And that is also the inverse. So these two problems, D and E, are taking them from exponential form and putting them into logarithmic form, or taking them from logarithmic form and putting them to exponential form. F, same type of problem. We're logging a variable. Anytime you're logging a variable, you should automatically think put it into exponential form. So this log here has log base 10 since there's nothing listed. So you start with the base, it's going to be 10, and then to the negative 1 power is equal to x. And you can see right here we have 10 to the negative 1 equals x. Under the solution, you can see 10 to the negative 1 becomes 1 over 10 to the first, which is 1/10. And the last one to this part is log base 3 of x equals 4. Once again, the variable is being logged. Therefore, you're going to move it from logarithmic form into exponential form. This is log base 3. So we're going to start with the base 3. It's 3 to the fourth equals x. So you can see x equals 3 to the fourth, and 3 to the fourth is 81. Now, here are a few strategies that we used in example 1, and they're summarized here. So strategies for solving exponential and logarithmic equations. The first one is to rewrite the original equation in a form that allows the use of the one-to-one property of exponential or logarithmic functions. And what that means is, if you go back here to the previous screen, you can see when we had 2 and then 32, we rewrote the 32 so the bases matched. So we were able to then set the powers equal to one another. And that's a very, same with part C here. You can see we have this 1/3 and we have this 9. That's a very common strategy to solving these, and it works a lot of the times. Part 2, they asked you to rewrite an exponential, or they said you can rewrite an exponential equation in logarithmic form and apply the inverse property of logarithmic functions. And 3 is very similar. You rewrite a logarithmic equation in exponential form. So 2 and 3 are basically telling you to use that very first property of logarithms that we learned and just change its forms. You can go from exponential to logarithmic form, or go from logarithmic form to exponential form, and that should allow you to solve your equation. So these are actually equations. So we're going to solve each equation and approximate the result to 3 decimal places if necessary. So we're going to start with this one, this e to the negative x squared equals e to the negative 3x minus 4. So the original equation is that. And the nice thing with this original equation is that the bases already match, excuse me. So once the bases already match, we can utilize the one-to-one property to then set the powers equal to each other. So you can see I wrote negative x squared is equal to negative 3x minus 4. From there, I don't know if you recognize this or not, but this is a quadratic. And so to solve a quadratic, you're simply going to move all the terms over to one side. In this case, I moved the negative x squared to the other side, and we ended up with x squared minus 3x minus 4 equals 0. And that is able to be factored into x plus 1 times x minus 4 equals 0. And you're going to set each part of the factorization equal to 0, and you're going to solve, and you're going to get x equals negative 1 and x equals 4. So there's your solutions. The next one, part B, is a little bit trickier. This one is going to utilize the one-to-one property as well. You can see we have 3 times 2 to the x equals 42. The first thing you always want to do is you want to isolate the base and its power. So if there's anything being added, subtracted, multiplied, divided out here over on this expression, you kind of want to always get that stuff moved to the other side. So in doing so, in this particular problem, we're going to divide both sides by 3. And when we do that, we end up with 2 to the x equals 14. Now, 14 is tricky because 14 cannot be rewritten as a power of 2. So the backup plan is, since we can't utilize the one-to-one property, because 14 is not a power of 2, we need to utilize the very first property where you take things from exponential form and put them into logarithmic form. So that's exactly what we're going to do. This is an exponential equation, and you can see it's 2 to the x equals 14. The 2 here is the base of the exponent, so the 2 is going to become the base of the log, and the x and the 14 are going to switch. And you can see when I do that, don't really pay attention to this first part right here. This should have said x equals log base 2 of 14. You can kind of scratch this part. So taking this, going from exponential form to logarithmic form, gives you x equals log base 2 of 14. All right, guys. From there, you're going to utilize your change of base formula, which allows you to take log base 2 of 14 and rewrite it. You can rewrite it either as natural log of 14 over natural log of 2, or you could have just written log of 14 over log of 2. It's either way is going to be fine. It's going to give you the same answer. And the answer to that is approximately 3.807. All right, guys, that's it for today. There is actually no practice problems. I'll give you guys a little bit of a break, and I'll be back with you on Friday. Have a good day.